Hello everyone, I am Dr. NAVNEET KAUR, Associate Professor in Department of Electronics and Communication Engineering, Sagar Institute of Research and Technology, Bhopal. Today I am taking my 7th lecture of subject Digital Signal Processing. In my previous lecture, I had discussed about the concept and the formula of Z-transform. In my previous lecture, we had solved some numericals also related to Z-transform. Now, in this lecture, we'll be discussing the properties of the Z-transform. Now, the first and important property of Z-transform is linearity property. Now, according to the linearity property, if suppose we have two signals x1n and x2n, x1n is having Z transform x1z and x2n is say having Z transform x2z. In that case, if we have another signal xn, which is a1 x1n plus a2 x2n, that means x1n is multiplied by a1 and x2n is multiplied by a2n, and then they both are added. If this signal is calculated for Z transform, then the Z transform should be A1 x1z plus A2 x2z. That means the Z transform of x1n is multiplied by A1, Z transform of x2n is multiplied by A2, and then both are added. It means linearity property depends upon the superposition principle. The signal should satisfy superposition principle. That means the system should have a homogeneity property as well as scaling property. Now we'll move on to the proof of this property. Now, starting with the formula for Z transform xz, which is summation n is equal to minus infinity to infinity xn z raised to power minus n. Now we know here we want to find out the Z transform of a1 x1n plus a2 x2n. So instead of xn, we will write this expression. So here we have a1 x1n plus a2 x2n, and then according to the formula we have z raised to power minus n. Now we know that the summation of the sum is same as the sum of the summation. That means we can separate these two terms. So a1 x1n, n is equal to minus infinity to infinity, z raised to power minus n will form the first term, and a2 x2n will form the second term. Now, since we know that this summation is dependent upon the variable n, and a1 and a2 are constants, so they can be taken outside the summation side. Now here it is a1. Now this expression in the summation, it represents the Z transform of x1n, which is given by x1z. And this expression, it represents the Z transform of x2n. So it is represented by x2z. So it is given by a1 x1z plus a2 x2z. So this is the property which we wanted to prove. Here in this case, in linearity property, the combined ROC is the overlap or intersection of the individual ROCs of x1z and x2z. That means if I want to find out the ROC of the signal xz, then I have to find out the ROC of x1z and ROC of x2z, and then the common region of the two ROCs will form the ROC of xz. Now I'll enable my pointer options also, because in these slides I need to write somewhere. So next is the property time shifting. Now, according to the time shifting property, now we know that if xn is having Z transform xz, then if we are shifting our signal xn by k units, that means here we are doing time shifting. In that case, the Z transform will be xz z raised to power minus k, where this minus k is the units by which this signal xn is being shifted. Here, the ROC of this z raised to power minus k xz will be same as that of xz, except for z is equal to 0 if k greater than 0, and z is equal to infinity if k less than infinity. Because if k is greater than 0, then z raised to power minus zk can be written as 1 upon zk. So in that case, if z will be 0, the whole term will be infinity. So it will not be included in ROC. And when, if k is less than infinity, then it will be z raised to power k. So in that case, if z will be infinity, so it whole term will become infinite and it will not be included in the ROC. Now, next we'll move on to the proof of this property. So we will start with the left hand side. We want to find out the z transform of xn minus k. So putting this signal in the formula of the z transform, n is equal to minus infinity to infinity xn minus k z raised to power minus n. Now, here z raised to power minus n term is only there. What we will do, we will multiply it with z raised to power k and z raised to power minus k. We know z raised to power k and z raised to power minus k, it forms 1. So multiplying with 1 makes no change. So what I'll do, I'll merge z raised to power k here with z raised to power minus n, and z raised to power minus k I will take separately. Now this summation, it depends on variable n. So z raised to power minus k is constant. So it can be taken out of the summation sign and the rest of the terms will be in the summation. So z raised to power minus k is taken outside. So summation xn minus k z raised to power minus n minus k. Now, if I'll put n minus k as m, I'll substitute here as n minus k is equal to m. Now, if I'll substitute here m, so z raised to power minus m will be written. Now, if I'm changing my variable, I'll have to change the limits of variable also. So if n is equal to minus infinity, m will also be minus infinity. If n is equal to plus infinity, m will also be plus infinity. So here the variable is changed to m very conveniently. So m is equal to minus infinity to infinity xm z raised to power minus m. Now this expression inside the summation, it gives the z transform of xn. So it will be written as xz and we have z raised to power minus k also. So this property is proved, which is xn minus k is having z transform z raised to power minus k xz. Now here the signal is being delayed. If I see signal is being advanced, that means we have signal xn plus k. In that case, the z transform will be xz into z raised to power k. So in case of delay, we multiply by z raised to power minus k, and in terms of advance, we will write z raised to power plus k. Now next property is the scaling in the z domain. Now scaling in the z domain, property says that if xn is having z transform xz and the ROC is between R1 and R2, in that case, if I multiply by xn by some constant raised to power n, so here we will have a raised to power n xn is having z transform x z by a. That means this a is getting here divided. So x z upon a. And what will be the change in the ROC? Here ROC was previously between R1 and R2. Now it will be between AR1 and AR2. Right? So here a can be real or complex, but it is a constant number. Now we'll move on to the proof of this property. So we will start with the definition of the Z transform. We want to find out the Z transform of a raised to power n xn. So instead of signal xn, we will write a raised to power n xn z raised to power minus n. Now here we have a raised to power n and z raised to power minus n. Both are having n in the power. So we will combine here. So we will xn a raised to power n z raised to power minus n. So we will take common minus n here. So a raised to power minus inverse z raised to power minus n. Now here a inverse z means that we can write it as z upon a because it is having a raised to power minus 1. So z upon a raised to power minus n. So here we can see that this represents the formula for the Z transform, but the only thing is that in place of Z, we are having Z upon A. So instead of writing XZ, we will write XZ upon A. So we will write XZ upon A here. So this is the property which we wanted to prove. So if we want to find out the Z transform of A raised to power n xn, then it will be having Z transform X Z upon A. Now we will move to the next property. Time reversal property. Now, if we are having any signal Xn, which is having Z transform Xz and ROC is between R1 and R2, then if I'll take the time reversal of this signal Xn, that means instead of Xn, if I take X of minus n, then I want to find out the Z transform of this time reversal signal. It will be XZ inverse in place of XZ. That means Z will change to Z inverse. And what will be the change in the ROC? Previously, the ROC was between R1 and R2. Now, after time reversing, the ROC will be between 1 upon R2 and 1 upon R1. Now, we will move on to the proof of this property. We will start with the Z transform of X raised to power minus n. This is the formula for Z transform. So in place of the signal xn, we will write the signal x raised to x of minus n z raised to power minus n. So next, what we'll do, we will put the substitution here. Instead of minus n, we will take L. So L is equal to minus n. Since we are changing the variable from n to L, the limits will also change. So when n is equal to minus infinity, which was the lower limit, L will be infinity. And when n is equal to infinity, L will be minus infinity. So here, the limit will be L is equal to infinity to minus infinity, XL z raised to power L. Now, since we know that in summation, we will take lower value in the lower limit and higher value in the upper limit. So I can write it as L is equal to minus infinity to infinity without changing the meaning of this expression. XL. Now this is Z raised to power L. I can write it as Z inverse raised to power minus N. Now this also represents the formula of the Z transform of Xn. But only difference is that instead of having Z, we are having Z inverse here. So we initially, in place of Z transform, we write XZ. But since we are having Z inverse, we will write XZ inverse. So this is the property of time reversal, which we wanted to prove. So here it is proved. Now, next property is differentiation is in Z domain. Now, if we are having any signal Xn, which is having Z transform Xz, and I'll multiply this signal Xn with N, in that case, there will be a differentiation of this Z transform Xz. So I will write it as minus Z dxz upon dz. And there will be no change in the ROC of the signal after multiplying it with N. Now, we will start with the proof of this property. We'll start with the Z transform of NXN. So now, what we will do, we will find the formula of the Z transform, which is XZ, N is equal to minus infinity to infinity, Xn Z raised to power minus N. Now, what will I do? I'll take the derivative of both the expressions on both the sides with respect to Z. So dxz upon dz is equal to d upon dz of whole this expression. Now we can see xn is not having variable z. So this d of dz will be calculated for z raised to power minus n. So d of dz xn z minus n. Now xn is say independent of z. So it will be written as xn only. Now we want to find out the derivative of z raised to power minus n. Now derivative of z raised to power minus n with respect to z is minus n z minus n, z raised to power minus n minus 1. Now this minus n and xn will be taken together. Z raised to power minus 1 and z raised to power minus 1 will be separated. Now this z raised to power minus 1 is independent of n. So it will be taken out of this summation sign. So we will have z inverse and summation minus n xn z raised to power minus n. Now this minus sign will also be taken outside the summation sign. So we will have minus z inverse. Now this minus z inverse will be taken on the left hand side. So minus sign will go here and z inverse can be written as 1 upon z. So z will go here. So we will have minus z dxz upon dz on the left hand side. And on right hand side, we have only the term which is included in the summation. Now, if you see this term represents the z transform of xn. But the only difference is that instead of xn, we are having z transform of nxn. So we can write this right hand side as z transform of nxn. Now on the left hand side, we have this expression. So z transform of nxn is equal to minus z dxz upon dz. So we can write it as nxn is having z transform minus z dxz upon dz. So this is the property of differentiation which we want to prove. Here I have already told you that after differentiation, the ROC will not change. So the both will have same ROC. Now the next property is convolution of two sequences. Now according to this property, if we are having two signals, say x1n and x2n, say x1n is having z transform x1z and x2n is having z transform of x2z. And if I take the linear convolution of these two signals and I am finding the z transform of their linear convolution, in that case, the z transform will be the product of the individual z transforms, which is x1z into x2z. And ROC will be the intersection of the ROCs of these two z transforms, x1z and x2z. So now we'll start with the proof. First, we'll take left hand side, which is convolution of x1n and x2n. Now we know the formula for convolution. It will be k is equal to minus infinity to infinity x1k x2n minus k. Now I want to find out the z transform of xn, which is the convolution of these two signals. So I take xz as z transform of convolution, and the formula for convolution is here, which I have already mentioned in my equation number 2. So putting in the formula of z transform, instead of xn, I am having linear convolution of two signals x1n and x2n, which is represented by this formula. So in place of xn, I'll write the formula for linear convolution. So summation n is equal to minus infinity to infinity. I have linear convolution formula z raised to power minus n. Now x1k, x2n minus k, z raised to power minus n. Here the terms are written separately. So x1k is written with the summation k and rest of the terms are written with the summation n. Now in this term, what we have done, z raised to power minus n is there. What we'll do, I'll multiply it with z raised to power k and z raised to power minus k. We already know z raised to power k and z raised to power minus k, if they are multiplied, they will give 1. So multiplying it with 1 will not change this term. So z raised to power k will be combined with this z power and z raised to power minus k will be taken separately. This z raised to power minus k will be taken along with this summation. So here we can see x1k z raised to power minus k and x2n minus k z raised to power minus n minus k. Now in the second summation, we will take n minus k as m So since we are changing the variable, the limits will also change. Here we are taking n minus k is equal to m. When n is minus infinity, m will also be minus infinity. And when n is plus infinity, m will also be plus infinity. So here we will take n minus k as m. Here also n minus k as m. And m will be minus infinity to plus infinity. So this will be the product of the two summation. Now we know this is the formula for Z transform of x1n. And this is the formula for Z transform of x2n. So this is x1z and this is x2z. So this is the Z transform of xn, where xn is linear convolution of these two signals x1n and x2n. So Z transform of Z transform of linear convolution of x1n and x2n will be multiplication of x1z into x2z. And this is the convolution property. And I had discussed one also, ROC will be the intersection of x1z and x2z. Now this is all for today's lecture. We have already discussed important properties of the Z transform. Thank you.